Hello and welcome back. Today we're going to talk about logic. Logic is going to be sort of the basis for how we reason and how we make proofs. And so we want to, in a fairly quick and informal way, get through just enough logic so that we can justify some of our methods for making formal mathematical arguments. So let's just jump right in and start with the most fundamental thing, which is statements. So a statement or proposition is just a sentence which is unambiguously either true or false. And as a notational convention, we're going to use variables to refer to statements. Like we might use a P or a Q or some other usually we use lowercase letters, although we may use uppercase letters sometimes. But the idea is that we kind of want to turn, we want to be able to break sentences up into little pieces and label them with variables and sort of start treating the logical structure of sentences in sort of an algebraic way. So we want to have symbolic ways of expressing logical expressions, and then we're going to have some rules for how you can manipulate those expressions, sort of like algebra. So anyway, let's talk about this example here. So the first part of that example is the sentence 2 plus 3 equals 5. So the question is this a statement in this sort of logical mathematical sense? Is it a statement? Is it a sentence which is unambiguously true or false? Well, I think, yeah, this is definitely a statement. So I'd say yes. This is a statement, and not only is it a so if it is a statement, it has to be either true or false, unambiguously. And this is a true statement. Okay, the second example, Monday was a rainy day. Is this sentence unambiguously true or false? I don't think so, because there are lots of different Mondays, and sometimes it would have been a sunny Monday, and some days it would have been a rainy or cloudy Monday. So I would say no on this one, not a statement, because some Mondays are sunny, some are not. So I can't assign a truth value to this statement sort of universally, like no matter when someone says it. Like if someone said it this week, this particular week that I'm in right now, Monday was a sunny day, it would have been a true statement for this week, but if someone would have said it back in January, it probably would have been a false statement. So this sentence just isn't always either true or false. Its truth value changes depending on when you say it. Okay, the third example here, the derivative of x squared equals sine of x. I mean, the derivative of x squared is either sine of x or it's not, right? But it doesn't, like the derivative's value doesn't change depending on the day of the week or who says it or whatever. So here I'm going to have to say, yes, this is a statement, but it's a false statement, because it's not the case that the derivative of x squared is sine of x. The derivative of x squared is 2 times x, and we know that 2 times x and sine of x are not the same function. Okay, the next example, x is even. That depends on what x is. So if x had the value of 2, it would be true. If x had the value of 3, it would be false. So this sentence, this is an example of what we'd call a propositional function a little bit later, because it's a sentence that has a variable, and depending on the value of that variable, it can be either true or false. But this sentence, just as it is can't be sort of described as being universally true or universally false, or unambiguously true or false. It has ambiguity because we don't know what x is. So no, this is not a statement. And it's not a statement because different x values give different truth values to the sentence. And lastly, here the sentence, this statement is false. What do you think about that? This is an example known as a paradox. If the statement is true, then the statement must be false according to its own statement. So it's self-referential. This statement is false. Okay, so if this statement is true, then that means this statement is false. And if the statement is false, then according to the statement itself, the statement is true. So it's sort of like it can't be assigned a truth value unambiguously. I don't want to belabor this a lot. I think most of the time in math class, it's going to be pretty clear when you're dealing with a statement, because, we're going to be dealing with sort of objective, sort of mathematical structures. But in ordinary language, lots of sentences can end up not being mathematical statements because the truth value depends on maybe an opinion, or maybe it depends on the time at which the statement is said. So if you say it today, it's true, but if you say it tomorrow, it's false. It may have some variable in it, and as the variable changes values, the truth of the statement, the truth of the sentence changes. So there's lots of weird things that can happen in ordinary language that prevent a statement from being unambiguously true or false. And so most of the time in math class, we don't really have to worry about this, but sometimes we do. So the main thing is we're just trying to say, hey, we're restricting ourselves to sort of really concrete, really objective things. And in the world of logic, we're not going to try to take on things that are based on opinion and things that are too loosey-goosey, okay? So here's a point where you could pause the video and try your hand at these 6 sentences that I have listed here, and just try to decide for each one of them, are they statements or not? So in other words, does the sentence have an unambiguous truth value? And for the ones that are statements, maybe you can think about whether it's a true statement or a false statement. So take, a few minutes and do that on your own, and pause the video, and then come back and I'll put the answers down real quick. Okay, welcome back. So part A, yes, it's a statement. Now, is it a true statement? No. Sine of pi over 6 is actually 1/2. So this is a statement, but it's a false statement. Part B, is a differentiable function continuous? Well, the thing is, this isn't making a statement at all. This is asking a question, and questions can't be assigned truth values. So it's just no, it's not a statement. Part C, it is going to rain tonight. In the sort of mathematical statement sense, this is not a statement because its truth value isn't always true or always false. It depends on, again, when someone says it. So if someone says it the day of a day when it's going to rain, then it could be true. Otherwise, if you say it in the middle of summer in Seattle, it probably is going to be false. So this is just not a statement. It depends on when okay, when the statement is made. Part D, 2 squared plus 3 squared equals 17. Well, that's a verifiable claim in the mathematical sense, so yes. And is it true? 9 plus 4 does not equal 17, so no, it's false. Dr. Mann is a great cook. Well, I think it's true, but some people would say this is a matter of opinion. So matters of opinion are not the realm that we want to deal with, and so we're just going to say, no, this is not a statement. And then the last thing is a more complex looking thing, but it looks very mathy. And it says, if n is a natural number, then the sum of I from 1 to n is n times n plus 1 over 2. Yes, this is a statement. This is a thing that one can verify as either being true or false, and it won't change depending on the day of the week or whose opinion it is or whatever. And you may remember this actually is a true statement. This is a sum that you might have seen back in your calculus class. I won't offer a proof of it right now, but it is the sort of thing that could be proven to be true, and it's always true. Okay. So now, like I was saying earlier, what we're hoping to do is learn how to break down mathematical expressions into their sort of logical form. And so then we need to understand, how individual statements can be put together to form more complicated statements called compound statements. So before we get into that, let's talk about a little bit of notational conventions here. We're going to use T to mean true and big F to mean false, because we're talking about logic and statements are either true or false, right? So I want to be able to assign them these two values of T and F. And also, we'll represent statements with letters, like often we use like lowercase letters P, Q, R. This means we need starting from P. Or we might use capital A, capital B, capital C, etc. Again, the idea is we're trying to turn analyzing logical expressions into sort of an algebraic game. So to that end, let's start with the most simple sort of way of taking an existing expression and modifying it logically. And so that is called negation. So negation of a statement P, we'll denote that with a tilde P. Sometimes people use this sort of like a little crook P. I'm not sure what you call that little symbol. But in this class, we're going to use the tilde. So the negation of P denoted tilde P is just the statement forming the denial of P. So in other words, we call it not P. And it has whatever the truth value of P is, not P has the opposite truth value. So if P is true, not P is going to be false. And if P is false, then not P would be true. And that we can capture that in a truth table here on the right. So a truth table is just where we list all the possible truth values of the variable or variables in question, and then see what the corresponding new expression's truth values are. So P could be either true or false, indicated in that left column. And then not P having opposite truth value, the right column would be false, then true, like that. And so this table really captures what negation is, what it does and how we use it. And these little truth tables are really going to be our fundamental object for verifying, the truth values of logical expressions. But before we get into that too much, let's look at this first example here. So if P is the statement 2 plus 3 equals 5, then how would we express the negation of P? What's the denial of P? Well, we could just say 2 plus 3 is not equal to 5, or it's not true that 2 plus 3 is equal to 5, or something along those lines. So, symbolically, it'd probably just be easier to write it this way. 2 plus 3 does not equal with a slash through it, 5, like that. And we could do this same sort of game with expressions that are not very mathematical in nature. Like the second example there, P is the statement Seattle is the capital of Washington, which we know is a false statement. So then negating it, I would get the true statement, Seattle is not the capital of Washington. Okay, moving along. The next way that we'll modify logical expressions is to use the conjunctive and. So if we have two separate, sort of more basic logical expressions, we can connect them with and. The conjunction of P and Q, which is going to be noted by P wedge Q, or maybe we'll call that caret, sort of the upside down V shape, is the compound statement obtained by connecting P and Q with the English connective and. And a conjunction is only true when both of the individual statements involved are true. And we know this from ordinary language, right? I mean, for example, if I would say roses are red and violets are blue, in order for that statement to be true, it's understood that both of those things are true. Roses are red and violets are blue. It's not one or the other or something along those lines. In the first example at the bottom there, if I want to form the conjunction of the statement, Well, I've got two individual statements here. I've got P is 2 is even, and I've got Q is 2 is prime. Then the conjunction P and Q would read 2 is even and 2 is prime. I suppose I could shorten that down by saying 2 is even and prime, but you get the gist. I'm just putting the connective and in between the two individual statements. Let's take a look at a truth table for conjunction or and. So here we have there are two variables in the compound statement. So if I want to sort of generate all possible combinations of truth values of P and Q, what I can do is label the table like this on the first two columns. Under the P column, I'll do true, true, false, false in that order. And then under the Q column, I'll do true, false, true, false. And that gives all four distinct possibilities of the combination of truth values of P and Q. I got true and true, true and first one's true, second one's false, first one's false, second one's true, or they're both false. Okay, so now we understand that P and Q is only true when both P and Q are true. So it's only the first line of this truth table that P and Q is going to be true. In all of the other cases, P and Q is false because one or both of the individual statements P or Q is false. And one last little note here. I want to point out that but equals and. But is also a conjunction. The purpose of but is to just draw some sort of distinction between P and Q, the two things that you're putting but between. But it still logically works the same way as and. So if you run across a sentence with but in it, just keep that in mind. You're really talking about an and there. Okay. The next one that we'll talk about is disjunction, which is captured by the English word or. So what does disjunction do? Let's see. First of all, we have our notation for P or Q. There we're using the wedge, sort of the V-shape symbol. So that reads P or Q. And an or statement is only true, well, rather, an or statement is only false if both of the statements are false. So when you're doing an or, you only need one or the other of the two things to be true. It could be that both of them are true. So if I said roses are red or violets are blue, in order for that statement to be true, it only needs one of those two things need to be true. If it's true that roses are red, then the whole statement is true. It doesn't matter what happens with violets. Or if violets are blue, if that's true, then it doesn't matter whether or not roses are red is a true statement. So when we write down those possibilities in this truth table over here on the right, we'll do the same thing as before with putting the truth values under P and Q, like true, true, false, false, true, false, true, false. So that captures all the possible combinations of P and Q. And then the only way this thing is false with an or in between is the last line. If both of the statements are individually false, then the whole thing with an or in between it is false. Otherwise, it's true because at least one of the statements is true. So this example on the bottom left here, if P is the statement N is even, and Q is the statement N plus 1 is even, then P or Q would be the statement N is even or N plus 1 is even. Keyword being or here. I want to make a little note about something that's called exclusive or. So exclusive or is something you see in computer science a lot. So if you're a computer scientist or taking computer science classes, the or that you're familiar with there may not be exactly the same as the kind of or that we're using here. Exclusive or requires that in order for the or statement to be true, you can only have exactly one of the two statements involved being true. So oftentimes in ordinary language, we use or in the exclusive sense. For example, if you go to the counter at a restaurant and they ask you, would you like Coke or Dr. Pepper? You wouldn't say yes. They really mean one or the other. You either get Coke or you get Dr. Pepper. It's not both, right? So, and oftentimes in ordinary language, just from context, we understand the or to be exclusive, one or the other, but not both. But in the mathematical world, when we see ors, we're going to take the inclusive view of or, where when we say P or Q is true, we understand it could be that both of them are true. It's only necessary that one of them be true for the whole thing to be true, but it could be that both are true, and we're okay with that. So our convention is we use the inclusive or. So now we have negation and we have conjunction and, so we can combine two statements with and to get a bigger, more complicated statement, and we understand the logic of it. And we have or, another way, a disjunction, to combine two statements to get a bigger, more compound statement, and we understand the logic of that. Another fundamental way that we connect two statements P and Q is a conditional statement. So we do if then. If P, then Q. So if P and Q are two separate statements, then we can form the conditional statement just by saying if P, then Q. And we denote that by P arrow toward Q. And the key thing about a conditional statement is, how do you tell when it's true? Well, our convention, and it makes sense with how we ordinarily use if-then statements, is a conditional statement is true unless, except for the one case where P is true and Q is false. By the way, P is usually called the hypothesis. And Q is usually called the conclusion. There's some other fancier words for this too, but this is what I tend to use, hypothesis and conclusion, to describe P and Q respectively. So the only way that if P then Q is false is when the hypothesis P is true, but the conclusion Q is false. So if we put that into our truth table on the right over here, so we'll fill that in true, true, false, false under P, true, false under Q. So the only line where this thing is false is the second line down. That's where the hypothesis is true, but the conclusion is false. And then in all the other cases, it's true. We'll talk about the why of it in a moment. Sometimes it takes a little bit of thought to think about why this truth table actually makes sense. Like, why, if P is false and Q is true, do we get that the conditional statement P implies Q is true? But we'll talk about that in a moment. But first, let's talk about, just do a basic example. Okay, so in this first example here, we have two separate statements. P is the statement, n is an even integer, and Q is the statement, n squared is an even integer. And so then we form the conditional statement P implies Q by doing if n is an even integer, then n squared is an even integer. And we're not doing anything crazy complicated here. We just put the statement P right here after the if, and then we put the statement Q right here after the then. Another example of this, which may seem a little bit repetitive, but I have a reason for doing this second example. So we have two statements, which are both the sort of statements that you can verify as either true or false. So P is Olympia is the capital of Washington, and Q is the statement 2 + 3 = 5. So we can form the conditional statement P implies Q as if Olympia is the capital of Washington, then 2 + 3 = 5. Again, all we did was take the two separate statements. Olympia is the capital of Washington, put that after if, and then 2 + 3 = 5 came after then. So we've got P implies Q. Now that statement might strike you as a bit absurd. In ordinary language, this sentence doesn't make a lot of sense. I mean, it's a sentence that you can state it, but it doesn't really conform to what we really expect from P implies Q. If P then Q usually denotes that there's some sort of causation, like because P is true, it follows, it can be deduced that Q is true. But that's, in the formal logical sense, that's not necessary to have that sort of consequence, that you can deduce one from the other. It's certainly, there's no connection. The fact that Olympia is the capital of Washington, certainly it doesn't follow from that 2 plus 3 equals 5. Nevertheless, in a strictly logical sense, Olympia is the capital of Washington here. That's a true statement. And 2 plus 3 equals 5 is a true statement. So our P is true and our Q is true. And so if we think about that in terms of the truth table up here, it corresponds to the top row. It is a true statement to say that if Olympia is the capital of Washington, then 2 plus 3 equals 5. But it seems absurd because there's no, it doesn't really follow from the fact that Olympia is the capital of Washington that 2 plus 3 equals 5 in the ordinary way we use if then. So this is just an example that points out that if then as a formal logical structure does not imply causation or that you can deduce Q from P, okay? So you can form these sort of English sentences that seem silly. This doesn't come up that much in mathematics, but it can. These sort of things, like you can have a true statement that's essentially unprovable, it turns out. And so you can form the sentence if then, but it's not something that you can actually prove, I guess. So a couple discussion points. So what's the deal with the truth table for P implies Q? So let's revisit the truth table up here. Why does that truth table make sense? One way that I like to think about it is, under what circumstances would I be a liar if I utter the statement, if P then Q? In ordinary language, if I make an if then statement, it's kind of like I'm making a little promise that if P is satisfied, if it's true, then it better be the case that the Q part is true. For example, let's say that my statement P is, I win the lottery. And let's say the statement Q is, I'll give you $1,000. So the statement in total is, if I win the lottery, then I will give you $1,000. So I can examine the truth values of the two parts of that if-then statement. The P part is I win the lottery, and the Q part is I give you $1,000. Now in this statement that I've made, I'm only promising to give you $1,000 in the one instance where I win the lottery. So if I win the lottery, if that's true, then at the Q part, I give you $1,000. If I actually do give you the $1,000, then I wasn't a liar. So the total statement that I made, if I win the lottery, then I'll give you $1,000, is true. If I win the lottery, if the P part is true, so we're thinking about the second line of this table. So if I win the lottery, the P part is true, but then I don't give you the $1,000, that's when I'm a liar. And that's why the second line of this table is false. So I won the lottery, but I didn't give you the $1,000, so that made me a liar. So P implies Q part is false. Now the last two lines of this table correspond to the case where I don't win the lottery. Well, in the case that I don't win a lottery, I haven't made a false statement, right? So I uttered the statement, if I win the lottery, then I'll give you $1,000. If I don't win the lottery, then I'm not obliged to give you $1,000. I could go ahead and give you $1,000, and that would be this third line of the table, or I could not give you $1,000. That would be the fourth line of the table. Either way, though, I'm covered. I didn't promise to give you $1,000 if I don't win the lottery. So either way, the statement, if I win $1,000 on the lottery, or I'm sorry, if I win the lottery, I'm going to give you $1,000. I've told the truth. I haven't lied if I didn't win the lottery. I still don't have, it doesn't make a difference whether I give you $1,000 or not. So that's one way to think about that table. This example here where we talked about the Olympia being the capital of Washington, implying that 2 plus 3 equals 5, relates to this. for now, we're going to talk about this a little bit more later, but for now, I just want it to be clear that, so this is a logical structure here, let me call it a logical form. And you shouldn't think too much about whether the whole statement P implies Q makes sense, okay? Or whether it's something that's verifiable. Now, this on the other hand, so this is what we'd think of as more like the truth of Q can be deduced as a consequence of the truth of P. So in other words, when I do this P with a double barred arrow toward Q, what we're talking about is that we can prove it. We can prove that the truth of P implies the truth of Q. Notice that I'm talking about the truth of these two things too. So I'm really only focusing on one line of the table, the truth table. I'm focusing on the first line of the truth table. And I'm saying can be deduced. So that indicates that there's like some line of logic that connects the truth of P to the truth of Q. So this is a sort of a heavier statement here where you have the 2-bar arrow. It's saying something about we can prove it, we can verify it, that one follows from the other. Whereas the one on the left is not saying anything about whether it's provable or whether it's true or false. It's just a formal logical structure, okay? So it's difficult sometimes to separate the ordinary language of the phrase if this then that from what we accept that it means logically. And what we accept that it means logically is just this truth table up here. The truth table up here says, well, we can analyze that in terms of the truth values of the constituent pieces, the P and the Q, and it's just a formalism, okay? I think I've dwelled on that for long enough. Let's go to biconditional statements, and this will be the last sort of way that we'll build more complicated compound expressions from simpler expressions. So biconditional statements, when you say them in English, so if P and Q are statements, then we would say P if and only if Q is a biconditional statement. But what does that even mean? Well, the next way that we word it gives you a sense of what it means. Another way to say P if and only if Q is to say P is equivalent to Q. And we use this notation over here, P with a double arrow at Q. Another notational shorthand we use is we use IFF to indicate if and only if. It's just an abbreviation. I want to think about equivalent. So if we're talking about logical expressions that have truth values, when we say P and Q are equivalent, what we really mean is that they have the same truth value, okay? So P if and only if Q is going to be true exactly when P and Q have the same truth value. And so that tells us what the truth table ought to look like. So if we fill in our true, true, false, false, and true, false, true, false under Q, then the lines of this table where P and Q have the same truth value are the first line and the last line. So those are the instances where P if and only if Q is true because P and Q are equivalent in those two cases. In the other two cases, the middle two lines, P and Q have opposite truth value, so they're not equivalent. So I'd have false on those two lines. So just a little note here. So P if and only if Q being true means P and Q have the same truth value. And then P if and only if Q equals false means P and Q have opposite truth value. So just as a quick example, if P is the statement 2 plus 3 equals 6 and Q is the statement 7 is prime, then P if and only if Q would read 2 plus 3 equals 6 if and only if 7 is prime. Now we can actually assign a truth value to this because 2 plus 3 equals 6, we know that that is a false statement, and 7 is prime we know is a true statement. So this is true and this was false. Those two statements have opposite truth value, so that means I know the whole thing is false. In English, we have lots of different ways to phrase if P then Q. or P if and only if Q. And in this box in white here, I have listed several that I know of. There may be others that I haven't listed. So let's just go down the line here. So the first one here is just the standard way of saying P arrow toward Q means if P then Q. But we can also say P if P then Q is the same thing as saying P only if Q. But we can also say P implies Q as Q if P. So even though in the sentence Q came before P, it's still P implies Q. By the way, that's another way to say it. P implies Q is another way to say P arrow Q, or if P then Q. Another way to say if P then Q is to say P is sufficient for Q. But yet another way to say P implies Q is to say Q is necessary for P. Notice that again, this is an instance where Q comes first in the sentence, even though it's P if P then Q. So Q is always, in all these examples with P implies Q, Q is the conclusion, okay? So the conclusion can come first in the sentence depending on how you worded it. And then the last three have to do with if and only if. So here we have just the double arrow means if and only if. Another way to word that is with, you can say P is necessary and sufficient for Q, or you can say P is equivalent to Q. We've mentioned that one already. A few of these are a little confusing. I want to focus on at least one of them. I think the one that's most confusing to students is the second one here. I'm sorry, yeah. P only if Q. Like when you compare that to Q if P, like this needs some examination here, these two. Let's go to this first example at the bottom here. I want to compare these two sentences. The first one is, I eat if I'm hungry. And then the second one is, I eat only if I'm hungry. Now you could easily get those confused in ordinary English and think maybe that they kind of mean the same thing, but they actually sort of have the opposite meaning in terms of what's the conclusion and what's the hypothesis. So in the first one here, it's more like the third line of this white box up here. You've got something, a P, and then if, and then a something else. So I am hungry is your P, and I eat is your Q. So this is P implies Q when you think about it that way. So what it's saying is that if I'm hungry, then I eat. So let me just go ahead and label this here like this. This sentence is P implies Q. Because the if part, like what is the hypothesis? What's the part that comes immediately after if? That's the I am hungry. If I am hungry, then I will eat, is how that translates. On the other hand, I eat only if I'm hungry. Okay, so now putting that only on it makes it a little stronger. It's saying, okay, if you see me eating, you know I must have been hungry to start with. I mean, like the only way that I'm eating is if I'm hungry. So if you see me eating, it implies that I'm hungry. Not the other way around as in the first sentence where, okay, if I'm hungry, then I eat. So in that first sentence, if I'm hungry, then I eat. I might also eat if I'm not hungry, right? Like I might go, well, I'm just doing some pleasure eating here. I'm not really hungry, but I'm eating an ice cream anyway. So it's not sort of necessary to be hungry. It's just a condition. Like if I'm hungry, then I eat. But I might also eat if I'm not hungry. But when you say it the second way here, I eat only if I'm hungry, really what that's doing is I'm hungry is the conclusion. So this one, well, maybe I should label it the opposite way. Let me call that. Let me make the labeling match what I had before. So if this is Q and this is P. So now we're talking about Q implies P. The fact that I'm eating implies that I'm hungry is what this sentence is trying to say. Okay, and let's look at this second example. So I want to find what is the logical form of the following sentence. Here's the sentence under consideration. In order for n to be even, it is sufficient for n squared to be even. What is sufficient? So if we think about, if we go up to the table, P is, so on this line right here, one way to say P implies Q is P is sufficient for Q. But notice that it's the P that is sufficient, right? Sufficient is referring to P. So whatever the sufficient part is the hypothesis, and then the part that comes after is the Q. So what is sufficient? It is sufficient for n squared to be even. So n squared being even is going to be your P, your hypothesis, and then it is sufficient, n squared being even is sufficient for n to be even. So what this sentence really translates out to is, if we put P to be the statement n squared is even, and Q is the statement n is even, then the above sentence is P implies Q. If n squared is even, then n is even. So as you can see in this example, you have to sort of sometimes carefully parse these sentences to understand what the actual logical structure is. I don't think it's completely obvious, like what's the hypothesis and what's the conclusion when you read it this way, at least when you're sort of new to this. Luckily, most of the time, mathematicians try to avoid too ambiguous of language, but sometimes when you're reading math textbooks, you do see this kind of language. And so you just need to be, when you start seeing these words necessary and sufficient, you need to figure out what is necessary, what is sufficient, and identify those modifiers in the sentence and what they apply to, so that you can figure out what the hypothesis and the conclusion are. All right, so let's do a little skills check here. So this is a point in the video where I want you to pause and try to do the exercises below. So in this box here, there are 5 sentences. And what I want you to do for each of those sentences is to identify the logical form by sort of labeling different parts of the sentence with a variable like P or Q or R. And then saying, okay, after you've got the parts labeled, then it's of this form, P, arrow, Q, or something along those lines. So take, however long it takes you to do this, push pause on the video and just see what you can do. And when you come back from the pause, I'll work a couple of these with you. All right, welcome back. So now, let's start with part A. I'll do part A and then I'll do part D. Okay, so for part A, I would do P is the statement, roses are red. And then I would do Q is the statement, violets are blue. I'm not sure why I capitalized red there, but. And then the logical form of the original sentence is, it was P and, so that little upside down, that caret symbol, Q is the logical form. And for part D, I have one part that says a squared plus b squared equals c squared. And then I have a part that would be a is even. And then I have a part, let's call it R, that would be b is even. B is even. So then what is the logical form of this thing? So what's the hypothesis and what's the conclusion? A necessary condition for a squared plus b squared equals c squared is that so what is the necessary thing in this? So what is necessary? A necessary condition is this stuff. So the thing that necessary is applying to is a is even or b is even. Okay? So when we go back to the table on the previous page, we see that language Q is necessary. The thing that's necessary is the conclusion, Q. That tells me that A is even or B is even as the conclusion. And then the other part is going to be the hypothesis. So that tells me how to structure this thing. The hypothesis is the a squared plus b squared equals c squared. So the logical form is P and then implies, and then Q or R was the conclusion. So Q or R, like so. So this is really cool. You see what we're doing here? We're taking sentences and converting them into these like almost algebraic looking expressions. And then what we're going to find is that there are rules that would allow us to sort of algebraically modify these expressions into equivalent forms, which is very powerful. Just like in algebra class, you know, when you see something like, you get something like x squared plus whatever, 3x plus minus 4 or something like that. Like, you know, you might be able to factor that and change it into an equivalent expression. We want to do similar sort of things with our logical expressions. We'll get there soon enough. So the next thing to talk about are the converse, inverse, and contrapositive of a conditional statement. The converse of if P then Q is if Q then P. So whenever you just reverse the hypothesis and the conclusion, the resulting object is called the converse. The inverse of P implies Q is not P implies not Q. So this is just negating the hypothesis and negating the conclusion and keeping things in the same order though. And then lastly, the contrapositive of P implies Q is not Q implies not P. If not Q, then not P. So here you're reversing the order and negating everything. Whenever we're studying mathematical things, I feel like we often consider the converse. Like anytime you can prove a statement of the form P implies Q, it's natural to ask, can you reverse the logic? Is it true that Q implies P? So we just have a word to refer to that sort of thing. The converse comes up quite a bit. The contrapositive, the third thing there, is really important because we're going to come to find out a little later, we'll see, is that P implies Q is logically equivalent to not Q implies not P. So these two things have the same truth value. So if I can prove this thing over here, if I can prove the contrapositive, then at the same time I will have proven the original conditional statement. So that gives rise to a method of proof called proof by contraposition. The inverse doesn't come up that much in my experience, but I guess it comes up enough that we have a word for it. In any event, right now we're not going to think too deeply on it. It's just a matter of modifying the original implication. So we have in this example here, we have a sentence, and I want to write down the converse, inverse, and contrapositive of it. So a necessary condition for x squared plus 3x plus 2 to equal 0 is that x equals -1. First thing we need to do is think about the logical form of this. Let's identify the bits and pieces first. So if we set P equal to x squared plus 3x plus 2 equals 0, and Q is x equals -1, then the logical form of the original expression is P implies Q. Because what is the necessary condition? The thing that is necessary, whenever you say Q is necessary for P, that's the P implies Q bit there, right? So whatever is being referred to as necessary is the conclusion. When I go back to the sentence we were working on here, necessary refers to x equals -1. So the necessary part, in other words, the conclusion is x equals -1. And so that's why I've got that in the conclusion here. Okay, so now we know the logical form, and so then the rest of it follows pretty easy. So the converse is Q implies P, which translates out to if x equals -1, then x squared plus 3x plus 2 equals 0. And the inverse is not P implies not Q, which we could write that as if x squared plus 3x plus 2 does not equal 0, then x does not equal -1. And then the contrapositive, now that's going to be not Q implies not P, which is going to be if x does not equal -1, then x squared plus 3x plus 2 does not equal 0. Now, I'm not commenting on the truth or falsity of any of these statements. This is just writing down different related logical forms to the original form P implies Q. Let's now think about truth tables. All a truth table is where we examine all the possible truth values of the given expression in terms of what the truth values of the constituent pieces are. So if I have two variables P and Q, I would look at all possible truth values in combination of P and Q and then see what the resulting truth values of the expression are. This is usually pretty straightforward to do. So let's just look at the first example here. Here's the expression. We want to figure out what are all the possible truth values for this expression sort of as a function of what the truth values of P and Q are. So we can do this just by making a table. The way I build up this table is first I write down what all the variables are. You got P and Q are the two variables. So you got P and you got Q. And then I can write down what all the possible combinations of P and Q's truth values are. So we've done this before. True, true, false, false. And then we got true, false, true, false. Okay, so now we want to build up that expression that we have here sort of piecemeal. I don't want to try to write it all down at once. I want to sort of build it up in terms of the pieces that it's made from. So, I've got a P implies Q inside there, and then I've got the negation of that. So I can kind of do that in two steps. Maybe I'll do something like this. I'll go, okay, I know the truth table for P implies Q from before, so I could write down those truth values. And then after I have that, I could negate it just by switching all the truth values of the previous column. Okay, now I have that bit, so I could do that in conjunction with Q. So I could do not P implies Q and Q. And that's the final expression, right? That's the thing that we want. So the object of the game here is get the truth values in the furthest right column. So, but we'll get there just by considering the ones to the left of it. So P implies Q, we remember, goes true, false, true, true. It's the only way P implies Q is false is if P is true but Q is false, and it's true in all other instances. Okay, then negating that would be false, true, false, false. And now for the grand finale, what I'm doing is I'm comparing the second to the last column to the second column. So I'm comparing these two, and I'm comparing them with and. So remember, when you're doing the and of two expressions, the only way the and statement is true is when they're both true, and it's going to then be false in all other instances. So I look at the second column and the fourth column, and I compare them with and the only way it's going to be true is if they're both true. So I'm going to have false on the first line. I'm going to have false on the second line. I'm going to have false on the third line. And I'm going to have false on the last line. So it turns out that this expression, not P implies Q and Q, is always false. Doesn't matter what the truth values of P and Q are. That expression is just always dead wrong. That's an example of what's called a contradiction. All right, let's do another example here. This would be a good time for you if you want to just see if you can do it on your own to press pause and then just try to do it. It's always a good idea. If you can work something on your own, or at least take a swing at it before you see me do it. But let's go ahead and do it. So this one's similar to the last example. I would start off, there are two variables, P and Q. So I got P and Q. Leave myself 4 lines underneath it. I know so it turns out if you have 2 variables, you're going to need 4 lines in the table. If you have 3 variables, you're going to need 8 lines, or 2 to the 3rd. If you had 4 variables, you'd need 2 to the 4th, 16 lines, and so on. So I got P and Q, and up here, I'm going to think about all the little bits and pieces in this expression up here. I see a not Q, so let me have a column for not Q. And then I've got P and not Q. I could go ahead and do right here. P and not Q. And then I've got a P implies Q. And then I need to negate that, so not P implies Q. And at this point, I've got this expression and I've got this expression, and I just need to connect them with an if and only if, right? So I can do that as the final column. All right, so let's do it. So true, true, false, false, true, false, true, false. Always starts the same. False, true, false, true. So now I'm comparing. So I'm doing P and not Q. So I'm comparing these two with an and. So they have to both be true in order to get a true. False, true, false, false. Okay, P implies Q would be true, false, true, false. Negating that. Oops, sorry. Should be true there. Then negating that, I get false, true, false, false. And then lastly, I'm comparing this column and this column with if and only if. Now remember, with if and only if statements are true if both of the pieces have the same truth value. And it's false if they have opposite truth value. So on this one, I'm going to have true on the first line because they're both false. I'm going to have true on the second line because they're both true. And then I'm going to have true here and true here. So this one turns out to always be true. This is kind of special when it happens. When a logical expression that's always true is called a tautology. And tautologies are very important. They're sort of like the things that tell us how to reduce things, like how to sort of change logical expressions algebraically, how to find equivalent forms of them. So like this, what this little tautology is telling us is that this expression, not P implies Q, always has the same truth value as P and not Q. So those two logical forms are interchangeable as far as logic goes, right? Here's a truth table that has 3 variables. So to do 3 variables, let me list those 3 variables, P, Q, R, and I'm going to need 8 rows to capture all the possible combinations. For P, to get all the possibilities, I'll do true, 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 false, 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 and then for Q, I'll go true, true, false, false, true, true, false, false. And for R, I'll do true, false, true, false, true, false, true, false. And if you think about it, those 8 rows, the way I've got them listed so far, gives all possible combinations of truth values of P, Q, and R. All right, so what's next here? So I need Q implies R, and then after that, I need just P and that. So I do P and Q implies R, and then that's the column that we need. All right, so for Q implies R, so let's think about this. For Q implies R to be true, that'll happen unless Q is true and R is false. So any of the lines where Q is true and R is false is where I have a false, and then everywhere else it's going to be true. So I only need to, so it's easier to think about what the false lines are first, because everything else will be true. So let's see, where is Q true and R false? Well, it happens here, and it happens here. And that's it. Those are the only two places where Q is true, but R is false. So then all the other lines are true. And now, all I'm doing is comparing the P column with the Q implies R column, and I'm comparing them with and. So that means they need to both be true in order to get a true. Otherwise, they're false. So the first line would be true, then it's false, then it's true, then it's true, false, 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 false. Okay, so there's an example of what you would do if you had 3 variables. And if you had 4 variables, you'd have to have 16 lines, and like the P column would be 8 trues and then 8 falses, and then you'd break it into 4s and then 2s and then alternate each one. These things aren't super hard to do. Here's an opportunity for you to, try some other practice examples. I don't think that I'm going to work out any of these for you. I think the examples that I've worked out so far are sufficient for you to sort of work on your own. But here's some ones if you just want a little practice to try your hand at it, then go for it. So, take however long it takes you to do as much of that as you want. Press pause and do that, and then come back. Okay, next up are tautologies and contradictions. So tautologies are a bit like identities that you might have learned in trigonometry class. It gives you a way to sort of convert one logical expression into another equivalent form, typically. And we'll get a lot of use out of these. And also among tautologies are sort of rules for how you make conclusions, how you draw inferences. So that'll be an important part of tautologies too. So what is a tautology? Well, a tautology is just a statement that is always true. So we've seen an example or two of this. So whenever you look at the truth table for a logical form, if it's all true underneath, that column of the table, then you've got a tautology. So how do you verify tautologies? Oh, and by the way, contradictions are just where it's always false. Contradictions and tautologies are just sort of opposites of one another. Of course, in some ways, we only really need to talk about tautologies because anytime you have a contradiction, if you just negate the contradiction, then you've got a tautology. So they're just two sides of the same coin. So the way that you verify a tautology is to use a truth table. So let's just do that for this example here. Tautologies that have that are biconditional statements are very special. These are the ones that act like identities. So in this tautology, it's saying the logical form P implies Q, if P then Q, is logically equivalent to not Q implies not P. In other words, this tautology is saying that P implies Q has the same truth value as not Q implies not P. So an implication is always logically equivalent to its contraposition. Let's just prove it real quick. We can do that with a truth table. So we just go, well, there's 2 variables here. So we got P, Q, and we're going to need not Q, and we're going to need not P, and then we're going to need not Q implies not P. We also need P implies Q. And then for the grand finale, we can connect those last 2 columns up with a if and only if. So we'd have P implies Q, if and only if, not Q implies not P. Okay, start the table per usual. Not Q would be false, true, false, true. Not P would be false, false, true, true. Not Q implies not P. So that's true, false, true, true. Then P implies Q goes true, false, true, true. And then you see these last 2 columns, they have the same truth value all the way down, so the biconditional connecting them is true all the way down. So there you go. Since this is all trues, that tells you that the logical expression at the top is a tautology because it's always true. And here's something that is a contradiction. So we can verify that using a truth table. Got 2 variables, P, Q, not Q, P implies Q, P and not Q. And then lastly, P implies Q and P and not Q. Just filling in the easy ones here. Okay, second to the last column here, we got P and not Q. So compare those two columns, and you get false, true, false, false. Remember, when you're doing an and statement, both columns have to be true in order to get a true. And now we're going to do the and of the last two columns. So it'd be false, 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 false. So there you see that this expression is false in every possibility, so it's a contradiction. Ooh, here's to verify a tautology that has three variables. And it's kind of interesting to see what this tautology is telling you. It says that you can kind of interpret it this way in terms of how you can use it to reason. It's saying if it's true that P implies Q, and then Q in turn implies R, then you can conclude that it's true that P implies R. So it's a transitivity thing, right? P implies Q because it, kind of goes through the middleman of Q. Anyway, we use that kind of reasoning a lot to stitch together a bunch of smaller implications to get a bigger implication. All right, so let's do this thing. So we've got three variables, P, Q, and R. So that means we're going to need 8 lines in our table. What else do we need? Well, we need P implies Q. We need Q implies R. We might as well do P implies Q and Q implies R at this point. And we need P implies R. And then lastly, we need... Now, if you ever start to run out of room in your table, one thing that you can do that will give you more room in your table is you can label things, like give them some sort of signifier. Like I could have done something like, let's call that bit A, and call that bit B, and call that bit C, so that in my table, to keep it a little more tidy in the horizontal direction, then I could put A, B, A and B, C, and then A and B implies C, just to keep things a bit. If some of these are really complicated, it can take too much room horizontally on the page. You don't have enough room to fit it, so you got to make some abbreviations like this. I think I could have fit this one, but I just wanted to show you that that's something that you can do if you like. Okay, so let me label in the P, Q, and R. That's just boilerplate. Okay, so A is P implies Q. So we're doing that implication right there between the first two columns. So again, an implication is only false whenever the hypothesis is true and the conclusion is false. So using that, I get this for column A. Then for B, I'm doing Q implies R, so that's the second column implies the third column. Using the same logic as before, this will be true, false, true, 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 false, true, true. Then I can do the and of those last two columns. So I've got to have both columns are true in order to get a true. So true, false, 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 true, false, false, true, true. Okay, C is P implies R. So first column implies the third column. True, false, true, false, true, 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 true. And lastly, I'm doing implication of the second to the last column to the last column that I've completed. So I only get false whenever it's a true implies false situation. So this will be true, 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 true. And there you have it. The expression in question is indeed a tautology because this worked out to be all truths at the end. So there are many important tautologies and contradictions, and some of them that you might find in books are summarized in these two theorems, Theorem 1.22 and Theorem 1.323 here. Theorem 1.23 are all contradictions, and then all of the ones in 1.22 are tautologies. And some of them are sort of the things that you would expect. Like, for example, Part B, Theorem 1.22, Part 1, Part B, just says when you do not P, it's just the same thing as P. They're equivalent. When you do P and P, it's just the same thing as P. And that comes up sometimes when you're making arguments that you end up with the same thing anded with itself. So you can kind of just drop one of them. Modus ponens is a very common rule of inference. So you can kind of think of modus ponens as telling you that if it's true that P implies Q and the hypothesis P is true, then it implies that Q is true. And that's sort of the logical basis for how we stitch together a number of implications. We start with some assumption, and then we show that that assumption implies something else, Q. So if we're assuming the assumption is true and we argue that assumption implies some other thing, Q, then it must be that Q is true. And then starting from Q, you might make some other deduction and say, well, something else, R, is a consequence of Q. And so then you can deduce that R must be true, and so on down the line until you get to whatever desired conclusion you're trying to get to. Modus tollens here is another rule of inference that it gives you a way of reasoning indirectly. It basically says that if you can argue that some assumption P implies some other fact Q, but then you also know that the opposite of Q must be true, then it must be that your original hypothesis P must have been false to start with. So that serves as a basis for something called a proof by contradiction, we'll see. And, De Morgan's law is more of like an algebraic move. It says when you negate an and statement, you just negate the individual pieces and change it to well, I guess that one says if you're negating an or statement, then you negate the individual pieces and it becomes an and statement. But also when you negate an and statement, you negate the individual pieces and it becomes an or statement. So it's sort of an algebraic move you can do on the logical form. Here's a nice one for how you negate implication. The negation of P implies Q is actually P and not Q. So lots of good things like that. There's some sort of symmetric property, commutative property, transitivity property for implication and by implication at the bottom. I like the distributive property F and G. We use that some. Like ors distribute over ands and ands distribute over ors. So most of these, you kind of just need to know, but if you ever need to reference these things, you've got your book, you can go back to them. But most of them are sort of natural. It's kind of like if you think it should be a rule, it probably is, and you can look it up here. All right, so you can verify any one of these properties just by making a truth table. In principle, you should be able to sit down and go through any one of these and prove that it's either a tautology in the first one or a contradiction in the second one. So that would be a good time for you to do a little skills check. So here's a selection of different ones from Theorem 1.22 that you could attempt to argue for yourself. So I would suggest to you that you press pause on your video now and take a swing at these. Maybe you don't need to do all of them, maybe just one or two. But practice doing some of these on your own a little bit and see how it goes. All right, welcome back. I think I will prove part B for you, and then I'll leave the rest just to do on your own. But for part B, I see two variables, and so I'm just going to construct a truth table with variables P and Q. And let's see, I need not Q, so I'm going to go ahead and put that in. I need P implies Q, and then I need to negate that, so not P implies Q. I need P and not Q. And then I need to connect those last two things with an if and only if. So not P implies Q, if and only if, P and not Q. This is a very important tautology for how do how you negate implications, which we'll end up using this one quite a lot because some of our proof techniques necessitate that you negate. If you're trying to prove an implication, if you do an indirect method, you'll end up negating it. So you have to know how to do this, and you use this tautology to do it. So let's put the boilerplate part in. True, true, false, false. True, false, true, false. Okay, not Q is false, true, false, true. P implies Q is true, false, true, true. Negating that, you get false, true, false, false. P and not Q. So that's comparing the first and third columns with an and. They have to both be true in order to get a true. So that's false, true, false, false. And now, to fill in the last column, I compare the previous two columns compared with if and only if. And remember, if and only if is only true if both things have the same truth value. So if they're both false, you get a true, or if they're both true, you get a true. So it's going to be true, 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 as expected. So some of the tautologies are useful for negating compound statements. Let's go back up to the list of tautologies that involve negation. Theorem 1.22, part 1, subparts F through I are very useful for negating things. So the first one tells you, so part F tells you how to negate ors, part G tells you how to negate ands, part H tells you how to negate implication, if then, and part I gives you a way of negating a by implication, or a biconditional. So those are the main properties we're going to use here. I suppose part B gives you a way to negate, do a double negation if you need that one, but that one's kind of obvious anyway. All right, so the way to go on these statements is to think about the logical form before you start negating things. Like here, if I labeled that as P, and I labeled that as Q, and this is OR, so then what we're looking at here is P or Q. So then we had a rule that said not P or Q is the same or equivalent to not P and not Q. So my negation would be not P, which would be 2 plus 2 is not equal to 4, or becomes and then we could just say 5, Q is 5 is even, so not Q would be 5 is not even. It turns out that not, if you're talking about an integer, you would just say 5 is odd. How about part B? So again, I think it would be helpful to label the parts of it with letters. So if Joe wins the lottery, so maybe I'll call Joe winning the lottery is the statement P, then he will buy a new car. He will buy a new car. That'll be, let's say, Q. And then this bit, he will take a vacation, would be R. So the logical form here is P implies Q and R. So then how do we negate that? Just in its logical form. Sometimes it's easier to do it in the logical form before trying to jump straight to the English form of it. Negating P implies Q and R. First of all, think about the fact that this is an implication. When you negate an implication, just like, so we have an identity or a tautology that says not P implies Q is the same as P and not Q. So this is what we want to convert. That we want to use this identity, the right hand side of it, to form that negation there. So this is going to become P and not Q and R. And then we can take that one step further because we know how to negate an and statement per one of the properties up there called De Morgan's law. to negate an and statement, you negate the individual parts and change it to an or. So this would become not Q or not R. So if I want to convert that into English, it would go something like this. Sometimes it's hard to think about the tense of it, like should I phrase it past tense, future tense? I'm not going to worry about that too much. Maybe I'll do like Joe won the lottery, and then we got the disjunction of not Q and not R. So it'd be and either this or that. So Joe won the lottery and he will either, maybe I should be careful not to use either. That kind of gives a sense of exclusivity to the or, which we don't have. And he will buy a new car, or he will not buy a new car. Got to negate it. He will not buy a new car, or he will not take a vacation. Okay. Moral of the story here on these two examples is that it's actually pretty useful to analyze the logical structure of the sentence, sort of convert it to a sort of algebraic form, so use variables P and Q and whatnot. And then once you've got it boiled down to that, apply those tautologies to form negations, and it gives you sort of an algebraically or tautologically equivalent way to express the sentence, and then you can convert it back into English. You should try your hand at some of these type of examples. And so hit pause and work on these. And then when you're done, come back and we'll work through one or two of them together. Welcome back. So let's work through one or two of these together. Now, one thing you need to be aware of as you're doing these sorts of examples is that the English language just has some sort of vagaries. I'm sure all languages suffer from this sort of thing. But sometimes it's not clear whether it's an if-then statement or just a standalone thing, a standalone statement, or sometimes you see words like but instead of and. It can be tricky at times. But the ones here I think are fairly straightforward. But as we sort of get into it a little bit more, and maybe on the homework you'll see sometimes some examples that are tricky just because, So you have to think about more than just like if you're looking for an if-then statement, you got to look for these like different ways of wording if-then, or if it's sort of implied, that sort of thing. All right, so let's look at maybe part B. So I'm thinking along these lines. If I say, let's make P be the statement, today is Saturday, and I agree technically P here is not really a mathematical statement because I can't really assign a truth value to this very easily. But for the purposes of working with logical structure, it's fine. Then the second part of part B, then I do not have to go to work. Maybe it would be better to just phrase this in sort of like a more positive form. Like Q would be, I go to work. So that the logical form is P implies not Q. In other words, today is Saturday implies that I do not go to work. And I agree there was the word have in here. I do not have to go to work, but as far as the logic part of it goes, that doesn't really matter, right? So now let's negate it. So the negated logical form is we need to do not P implies not Q. So according to the rule for how you negate an implication, that would be the hypothesis and the negation of the conclusion, which was not Q to start with. Notice there's a double negative there, so that's the same. That's just P and Q. And so now, in English, the negation would be something like this. Today is Saturday, and I will work, or I will go to work, or something along those lines, okay? The last topic I want to talk about on this video is the idea of logical consequence, or another word for that is called entailment in logic, and logical equivalence. The first thing I want to talk about is the difference between these arrows. I alluded to this earlier, but I want to come back to it. Remember this example? Well, we had a similar example. If P is the statement 2 + 2 = 4, which is definitely a true statement, and Q is the statement Olympia is the capital of Washington, which is also a true statement. So just observe P implies Q is true. So the statement that if 2 plus 2 equals 4, then Olympia is the capital of Washington. That's a true statement. But in ordinary English, it makes it seem as if somehow Olympia being the capital of Washington is a consequence, like a logical consequence of 2 plus 2 being equal to 4. But we know that really there's absolutely no logical connection between 2 plus 2 equals 4 and Olympia is the capital of Washington. So that makes the if-then logical form feel a little silly at times. But of course, no one would ever try to make a leap like this, right? Or make some sort of statement. But it just points out that you can make silly statements. Now, if instead of Olympia is the capital of Washington, it was some other mathematical statement, like maybe if I replaced that with the derivative of sine of x is cosine of x, then you'd be like, does it really follow that the fact that 2 plus 2 is equal to 4, does that somehow imply as a consequence that the derivative of sine is equal to cosine? I don't think so. So in order to establish that the derivative of sine is cosine as a consequence, I'd have to come up with a proof. And if I just can't find a proof, that doesn't mean there isn't one. It just means that I haven't proven it yet. So I would have to have some way to actually prove there is proof. And this really gets close to sort of like a really deep topic in modern mathematics. And it's the idea that you can make statements in a axiomatic system that are true, but you can't prove them. So to give a proof of an if-then statement, you got to sort of show there's a chain of implications connecting the hypothesis to the conclusion, typically. Now, that's how you would prove it directly. I don't think that you can. So I think probably this statement here is one of those sort of things, like it's true, but not provable. So I just want to say that, but we are not saying Q can be deduced as a consequence of P. So whenever we want to say that, that's what the double barred arrow is. P implies Q, so this double barred arrow thing like this, it does confer that meaning. So there's a lot buried into this word deduced. So what do you mean deduced? Well, deduced or proven or some synonymous term means that there's a logical justification for how you can conclude the truth of Q on the basis of the truth of P. And that's a big part of what this class is about. So it involved using rules of inference and other tautologies to justify your reasoning for how you deduced it. But I just want to point out, we do have two different notations going on that seem similar, but they have different meaning. Now, when you have this one, P double bar arrow Q, or I usually just say that P implies Q, okay? But when you have that, it's certainly true that regular old if P then Q is true also, but it doesn't go the other way. So if this is true, it implies that one's true, but not the other way around. The single barred arrow, you kind of just think of as like a logical structure, but you shouldn't get too caught up in the truth of it as an entire statement. Whereas with the double bar arrow, we are caught up in the truth of the implication itself. See, in the next example, we can certainly there's a logical form here, if P then Q. So if n is an even integer, then n squared is an even integer. But we can actually prove it. We can prove if P is true. Notice the is true part. So we're taking as we're saying suppose the hypothesis is true, then Q is true as a consequence. So since we can prove this stuff here, then we can say P implies Q like this. I don't want to belabor this point too much, but just understand that we have a couple different arrows in play. One of them is just a formal logical structure, and then the double barred arrow is more of making a statement about truth and about proof. Okay? So the symbols aren't interchangeable exactly. And we have a similar concern with the double arrow for by implication, the if and only if, and when we put a double bar on it. So the double arrow just means if and only if in a formal sense. But the double barred double arrow means the two things on either side of that have the same truth value. Another way to say that, so if I write P, then I put the double barred arrow Q, like so. So that means P and Q have the, so one way to think about it is this. It means P if and only if Q with the single bar is a tautology. This is probably the most concise way to state what we're talking about here. When you have this P if and only if Q thing is a tautology, it means that it's true. And when is an if and only if statement true? It's when P and Q have the same truth value. So that's all that the double barred arrow means really, is that the corresponding biconditional is a tautology. But that in turn means that the two statements have the same truth value. So for example, we have this tautology from theorem 1.22 that says not P implies Q if and only if P and not Q is a tautology, right? Just refer back to theorem 1.22. I can't remember what part of 1.22, but it's in there. So then that in turn tells me that I can write not P implies Q. Instead of saying is all that is a tautology, I can just say is logically equivalent to with the double barred arrow here, and then P and not Q, like so. All right. So why this is nice is because, you know, these two things have the same truth value. And it doesn't matter what P and what Q are. For any P and any Q, those two things have the same truth value. So if I run across a statement that's sort of written in the form that you have on the left-hand side, I can convert it to the form on the right-hand side and prove that instead, and I will have simultaneously proven the thing on the other side. So this is how we can use these rules of logic and these tautologies to justify sort of converting statements from this form to this form, and then if I prove it in this form, it's as good as proving the original. It's a pretty powerful idea that we will make a lot of use of. Okay, I think I will stop there with this first lesson in logic. And next, we're going to start talking about quantified statements, which has to do with sort of specifying a universe of variables for which certain kinds of statements called propositional functions are true. And these are going to be really the main types of things that we're going to be working with proving in this class. And then we'll be ready to start doing proofs. We'll have all the logic that we need. But we do have to learn how to, with these so-called quantified expressions, we need to learn how to manipulate them using tautologies, especially when it comes to negating them, because a lot of our proof methods are going to have to do with negating expressions. So we have to know how to negate expressions that have these so-called quantifiers involved. So that'll be our next task, and then we can really start proving things. All right. Thanks for joining me again, and we'll see you again soon. Bye.